Hi, my name is Amin from Max Planck Institute for Informatics, and in this video I'll be presenting our work titled as FaCT, Faithful Concept Traces for Explaining Neural Network Decisions. This work is a collaboration with my colleagues Sukrut, Jonas, and Bernt. Deep networks have shown remarkable performance across different tasks, yet understanding how they arrive at their decisions remains a challenge. In this regard, many attribution methods have been proposed to highlight the input regions that influence the model's decisions, effectively telling us where the model is looking. However, these methods do not tell us what semantic concepts the model has learned and uses for producing its outputs. Another line of work are concept-based explanations, which try to explain what concepts the model uses for making decisions. A potential concept, for example, can be the wheel concept. An explanation would then show which images activate the wheel concept the most and where exactly in those images this concept activates for. Having this concept defined, the next step is to measure how important is the wheel concept for the predicted output class. Therefore, we keep in mind these three aspects of a concept-based explanation: how the concepts are defined, how are they visualized, and how their importance to the output is measured. When considering the prior work, we found several limitations on each front. For concept definitions, we observed that many works have concepts restricted to be specific, come from predefined lists, or have limited spatial extent. When visualizing the concepts, many works rely on upsampling heat maps, which have shown to be unreliable, in particular for VIT architectures. Lastly, in many works, the concepts are not part of the model's inference and are rather extracted post-hoc, making it difficult to assess how much they contribute to the decision. To address all of these limitations, we propose a new model that inherently encodes concepts in its layers, having them shared across classes. On the bottom right, we see the wheel concept that is shared across the vehicle classes. We also see that concepts with simpler semantics can happen at earlier layers, such as the yellow concept on the top left. By having the concepts encoded within the forward process of the model, we ensure that the model is only relying on these concepts to make its decisions. We are then able to fully decompose every logit into individual concept contributions. Further, every concept can be faithfully visualized at input level. To achieve this, we use sparse autoencoders to have interpretable concepts. For the layers before and after, we use because layers. In short, because layers are nonlinear layers that can be summarized as a linear transform on a per input basis. As each because layer can be summarized as such, we can summarize the layers that use concept activations to produce the output logit as a dynamic linear transform. This decomposes every logit to concept contributions. We can do the same for the layers leading to concept activations. Therefore, no matter where we are in the network, we can faithfully trace the contribution of concepts to the output logit, while also faithfully visualizing every concept at the input level. We can now explore different layers and architectures. Here we see samples of both dense-net and VIT architectures in two columns for different layers. Notice how the concepts are shared across classes and can have different spatial size. It is of course important to have a quantitative measure for the consistency of our concept. Here we see two sample concepts, where the one on the right is consistently activating for the model, while the one on the left is inconsistent. For this evaluation, however, we find human annotations to not be a suitable choice, as shown in the two rows where the concepts are either not part of the annotation or don't match the annotation granularity. This motivated us to look for a stronger evaluation setup. We thus propose a new metric which measures the consistency of concepts in DynoV2 space, a model that has shown remarkable performance on semantics correspondence tasks. We can now compare our results to the baseline on ImageNet. We see that across architectures, our FaCT model is able to maintain competitive ImageNet accuracy, while also providing much more consistent concepts as highlighted by the y-axis. In the paper, we also show how our concepts are more consistent than concepts from prior work, and also how they are human interpretable through a user study. With our concepts evaluated, we then explore whether the concepts aid understanding the decision-making of the model. Here, we look at a misclassification case where the model is confused between the volleyball and basketball class. At first, we can apply existing attribution methods to each logit. While these methods highlight where the model is looking, this is not sufficient to understand what is confusing the confusion between the two classes. We can now go one step further and look at the confusion on the concept level, showing how each concept contributes to the logits. On the left, we see concepts that mutually contribute to both logits, such as the ball concept on the first row or the jersey concept on the second row. In fact, for the jersey concept, we can already see that the top activating images have both volleyball and basketball instances. To conclude, our work proposes a new model with a shared concept basis across layers, providing faithful output contribution and input visualization for every concept. Thank you.